This is a empirical and molecular formulas video for Regents level chemistry. So, molecular formulas, they are the actual formula of a compound, meaning that this formula reflects the actual number of atoms in each molecule. So we have 6 carbon atoms here, 12 hydrogen atoms, and 6 oxygen atoms. Remember that that's what those subscripts tell us, is how many of each element we have. So the empirical formula, on the other hand, is the most reduced form of the molecular formula. So here we have the actual formula for the molecular formula, and then the reduced formula is the empirical formula. So if we look at C6H12O6, we have a formula here that has a bunch of common terms, or terms with common factors. So 6, 12, and 6, they're all divisible by 6, right? So if we divide them all by 6, then that's how we get this formula. We divide 6 by 6 and we end up with an imaginary 1 here. 12 divided by 6 gives us 2 for the hydrogen, and 6 divided by 6 would give us another imaginary 1 for this oxygen. So to go from molecular to empirical, you just want to see what is the highest term that you can divide into all of these subscripts evenly. So in this case it's 6. So the molecular formula is always a multiple of the empirical formula. So if we take this empirical formula here and we multiply all these terms by 6, that could give us this molecular formula again. So this empirical formula could also be for a different compound. Let's say it was C2H4O. O2, sorry. This could be another molecular formula that has this same empirical formula, because if we take all of these and multiply them by 2, we'd end up with C2H4O. So the same empirical formula could be representative of separate molecular formulas. It's also possible to have the empirical and molecular formulas be the same. If we look at water, H2O, this has the same molecular formula and empirical formula, because this molecular formula that is the actual formula of water cannot be reduced, because we've got an imaginary 1 here. There's no term that we could divide both of these numbers by aside from 1, which wouldn't change the value. So this is both the empirical and the molecular formula. So if we take a look at a couple of examples here, find the empirical formula of C2H6. So what we want to do here is see what's the largest number that we could divide into both 2 and 6. So in this case, they're both divisible by 2. So this would be C with a 1 and H with a 3. So we don't write the 1s in the subscripts here. We're going to write this as just CH3. But this is our empirical formula of this molecular formula. Again, we're just seeing what the largest number we could divide into both of these subscripts is. In this case, it was 2. So again, this is the molecular formula up here, C2H6, is a multiple of this empirical formula. If we multiply this whole thing by 2, we'd get C2H6 and have the molecular formula again. So let's take a look at another example here. Find the empirical formula of C8H18. So we want to see what term is the largest number we could divide into both 8 and 18. So you just got to be a little careful here. You might think, well, 4, because 4 divides into 8, but 4 does not divide evenly into 18. So we can't use 4 as our divisor. So the largest number that can divide into both 8 and 18 is 2. So if we divide 8 by 2, we get C4. 18 by 2, we get H9. So C4H9 is our empirical formula. We can't reduce this any further. We've got much larger numbers here than we did before, but you're not always going to have 1s and 2s as the subscripts down here. In this case, 4 and 9 is the most reduced that it can be. And again, if we were to multiply this empirical formula by 2, we would get back to this molecular formula. So the molecular formula is again a multiple of the empirical formula. So if we look at another example, C2H3O2. This is not able to be reduced any further because we have 2, 3, and 2. We could try dividing everything by 2, but 3 is not divisible by 2. We could try dividing everything by 3, but obviously 2 is not divisible by 3. So there's no number that we can divide in here aside from 1, which again wouldn't change the value, that would give us a more reduced form. So if this is the molecular formula here, it is also the empirical formula. So in this case, this is both the empirical and molecular formula. So that is possible, like we talked about with the example of water. So what about finding molecular formulas from the empirical formula? Well, we have a compound here, SO2, which is an empirical formula. Again, this cannot be reduced any further. So SO2, and it tells us the molecular mass is 128 AMUs, or atomic mass units. So we want to look at SO2 and see what the mass of this empirical formula is. So in this case, sulfur has a mass of 32, and then oxygen has a mass of 16, and we've got two of them there. So the total formula mass here would be 64. Again, we talked about calculating formula mass. If you have any problems with that, check on a previous video. But 64, what do we have to multiply it by to get 128? That would be 2. So if we multiply 64 by 2, we get 128. So this step here, what we want to do is see, this is our formula mass for the empirical formula. What do we have to do to change it to be 128? Because that's the molecular mass of the molecular formula. So in this case, 64 times 2 would give us 128. What you can also do is divide the molecular formula, 128, by the empirical formula mass, which would be 64, and that would give us 2, and that tells us what number we need to multiply by to get the molecular formula from the empirical formula. So our original formula was SO2, and we said we had to multiply that by 2, so we're going to do the same thing here. Multiply it by 2, and that would give us S2O4. So S2O4 would be the molecular formula of the empirical formula SO2 with a molecular mass of 128. So if that wasn't clear, we'll try another example here. So we've got a hydrocarbon with an empirical formula of CH2 and a molecular mass of 84 AMUs. So we want to take CH2 and figure out what its mass is. So we have 12 is the mass of carbon plus 1 is the mass of hydrogen, and we've got 2 of them there. So that would make a total of 14 for the mass of the empirical formula. So we want to think, what do we have to do to 14 to get it to be 84? So we could divide 84 by 14, and that would give us 6. So we have to multiply this 14 by 6 to get 84. So 6 is our factor here, which means we have to do the same thing to the empirical formula. We're going to multiply it by 6 and end up with C6H12, and that would be our molecular formula. And again, this is a multiple. Remember, the molecular formula is a multiple of the empirical formula, so that's how we got this. So again, we just want to see what number do we have to multiply the empirical mass by to get the molecular mass of the molecular formula. And in this case, we got 6. Again, we could find that by dividing the molecular mass by the empirical mass to give us whatever number we have to multiply by. Multiply the formula by the same number and you end up with the molecular formula. So if we try one more example here, a compound has the empirical formula of Fe3O4, and again, we can't reduce this any further, so that is a good empirical formula. It has a molecular mass of 231 AMUs. So what we want to do is see what is the mass of Fe3O4, the empirical formula. So Fe has a mass of about 55.8, and there's 3 of them. So you can multiply that out, that gives you around 167, plus oxygen, which has a mass of 16, and we got 4 of those, so that would give you 64. So our total mass here is going to be around 231. It really would come out to about 231.5, but if we're just rounding to whole numbers here, we can call it 231. A lot of times on the Regents, they'll give you just the closest whole number in terms of AMUs, so we would just use 231 here. So if we've got 231 as the mass of the empirical formula, the molecular formula here also has a mass of 231. So all we'd have to multiply by here is 1, and we would still have 231. So what that means is that this Fe3O4 also needs to be multiplied by 1, which would just keep it the same. So in this case, we have the molecular formula and the empirical formula are the same. So again, that is possible to have the same formula, and because here the empirical mass and the molecular mass were the same, that tells us that the formulas have to be the same as well. So what we're going to take a look at now is a couple of practice Regents questions on the topics of empirical and molecular formulas. So, which formula is both a molecular and an empirical formula? Well, realistically, any of these formulas could be molecular formulas. But the trick is, which could be empirical formulas? And we said the empirical formula is the most reduced form. So we want to see which of these formulas can't be reduced any further, and that's going to be the one that's an empirical formula and could also be a molecular formula. Again, any of these could be molecular formulas, but only the one that's fully reduced could be an empirical formula. So if we take a look at this first one, C6H12O6, we already did this example. This is divisible by 6 for all of these terms, so this is not an empirical formula, because if it can be reduced further, it can't be an empirical formula, because the empirical formula is the most reduced form. If we look at C2H4O2, again, all of these are divisible by 2, so this can be reduced further, so therefore it cannot be an empirical formula. If we look at C4H8, this is divisible by 4 for both terms, therefore cannot be the empirical formula. If we look at C3H8O, this is not divisible by any common terms. We've got a 1 there for oxygen, so therefore it's not going to be able to divide by any common terms. This would be a molecular formula because it can't be an empirical formula because it can't be reduced any further. And it could also be a molecular formula because, again, all of these could be molecular formulas. So another Regents question. What is the empirical formula of a compound that has a carbon to hydrogen ratio of 2 to 6? So a ratio of 2 to 6, that means that for every 2 carbons we have 6 hydrogens. So that means that the molecular formula has some ratio of 2 to 6. It could be 2 to 6, it could be C4H12. As long as we maintain some 2 to 6 ratio here, that could be the molecular formula. But we're trying to find the empirical formula. So we essentially want to reduce these as far as we can go. So we see, what can we divide into both 2 and 6? Well, the only thing here would be 2. So if we divide 2 by 2, that would give us C with a 1, and 6 by 2 would give us H with a 3, so this would give us CH3. So CH3 would be the empirical formula. Again, it's important to be careful here. This is the carbon to hydrogen ratio of 2 to 6, which tells us carbon is 2 and hydrogen is 6. So they've got the backwards answer here. You just want to watch out for that. They've got the non-reduced form here. You want to watch out for that because this cannot be an empirical formula because it's not fully reduced. So one more Regents question here. If we have a structural formula here, we could also find out what the empirical or molecular formulas could be. So what we want to do is count up how many of each element we have. If we count up the carbons here, we got 1, 2, 3, 4, 5 carbons. Counting up the hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the formula here is C5H10. So C5H10, this is the actual structure of the formula. So this is going to be our molecular formula. The molecular formula is the actual formula. So again, the molecular formula and the empirical formula. So the first one here has to be C5H10, so we can eliminate these two answers. Again, we're just counting up the carbons and the hydrogens, and that tells us the molecular formula. For the empirical formula, we want to see how we would reduce this C5H10 into the lowest possible terms. So in this case, 5 and 10 are both divisible by 5. So if we divide these both by 5, we end up with CH2, which would give us answer choice 1. Alright, so I hope this was a helpful video on learning about empirical and molecular formulas. Feel free to take a look again and pause as you go through if you need to take a look at some of this stuff some more. Thank you.